All right, today we are starting Unit 3, so this is Lesson 1 out of Unit 3. In the textbook, this is Chapter 7, Section 1, and this lesson is going to be about graphing exponential functions. So we're looking at two content standards again for this lesson, and the first one is that we will be graphing exponential and logarithmic functions, showing the intercepts and the end behavior. We're also going to look at trig functions, probably not in this lesson though. That's just part of the content standard. The other content standard is using properties of exponents to interpret expressions for exponential functions. And the mathematical practice that we're going to focus on is constructing a viable argument and critiquing the reasoning of others. So we've already graphed polynomial functions, and in this lesson we're going to graph exponential growth functions and exponential decay functions. An exponential function or exponential growth or decay might be new concepts to you, but you should have seen them before in previous classes. We've seen asymptotes before. The factors of growth and the factors of decay are things you may have seen before in Algebra 1, but if not, then there's something that we're going to cover in this lesson. So an exponential growth function is a function that has some number to the x power where that number is greater than 1. These graphs are continuous, they are one-to-one, they are increasing. One-to-one means for every x value, there's only one y value. The domain is always all real numbers. The range of the parent function is always all positive real numbers. Sometimes this will change, but the domain never changes. The asymptote for the parent function, there's a horizontal asymptote on the x-axis, and the intercept is 0, 1, the y-intercept. So our first example is we need to graph the equation y equals 4 to the x power, and we're going to state the domain and the range. So the simplest thing to do for this is just to make a table of values and center it around 0. So use 5 points and have 0 be your middle point, and plug in each of the x values that you get into the equation. Get your y values. 4 to the 0 power is 1, 4 to the first power is 4, 4 to the second power is 16, 4 to the negative 1. These answers will always be reciprocals of each other. Notice 16 and 1/16 and 1/4 and 4 are reciprocals of each other. Then we're just going to come over and sketch those 5 points on our graph, make a smooth curve, make sure your graph does not cross over the x-axis. The domain is always going to be all real numbers, and the range for this function is all positive real numbers. You can't have any negative y values if you look at this function. Okay, here's a check your progress problem. Pause the video as long as you need. When you have your answer, go on to the next screen to see the answer. And our answer for this one is C. Hopefully you could identify that it was C just by realizing that C is the only one that looks like an exponential growth function, where B, since the B value of 3 is greater than 1. Okay, we're going to talk about transformations now. The transformations for an exponential function are the same process as transformations for any other kind of function. If you have an x minus h factor, if it's minus h, that's to the right. If it's plus h, it's to the left. The k is a vertical translation. If it's positive k, it goes up. If it's negative k, it goes down. And if you have an a in front, that tells you the orientation and the shape. If a is positive, the graph faces up. If it's negative, it faces down. If a is more than 1, the graph is stretched vertically. It gets taller, basically. And if a is between 0 and 1, then it's compressed vertically, which means it gets like squished down. So now, for example 2, we're going to graph a transformation function. We're graphing y equals 3 to the x power minus 2. And we're going to state the domain and the range. So the first thing we should look at is what's the parent function. This function came from the equation 3 to the x power, but then it was shifted down by 2 units. So if we just use the values, like we could do -2 up through +2 for our table, we would just find 3 to each of those powers and then subtract 2 from each of our answers. And you can see that we get these values, so now we're just going to graph those values on a graph. And each of these are obviously coordinate points: 3, 25, 2, 7, 1, 1, 0, -1, and so forth. So when we do that, we get a graph like this. This time, the normal horizontal asymptote is the x-axis, but since we are shifted down to, our new horizontal asymptote is y equals -2. We will never cross this line down here. The domain, again, is always all real numbers, and the range, this time it's every y value greater than -2. Okay, for part B of the example 2, we're going to look at the function y equals 2 to the x minus 1 power. So this time the shift is an h value instead of a k. And then we're also going to state the domain and the range. So remember that any time you have a power that is shifted left or right, if it's minus, it's shifted right. If it's positive, it's shifted left. So this is a shift of the graph 2 to the x power, shifted to the right by 1 unit. So just plugging in our different x values again, we get the y values, and then we're just going to graph the y values as coordinate points. So on the next screen, we see that graph. Notice that this graph would have hit at 0, 1 normally. Normally we would have had the y-intercept here, but it shifted right 1. So we go right 1 unit, and boom, we are touching that point. This graph was not shifted up or down at all, so it still has the same horizontal asymptote of 0. Again, our domain is always all real numbers, and our range, just like the parent function, 2 to the x by itself, the range is every y value greater than or equal to 0. Okay, we've got a check your progress problem, part A. We're going to look at the function 2 to the x power minus 4. When you have your answer, go on to the next screen. And our answer this time is C. This graph was shifted down 4 units. And notice this is the only one that is shifted down at all. For part B, we're going to look at the function 4 to the x minus 2 power plus 3. So we've got a shift in both directions this time. Pause the video, and when you have your answer, go on to the next screen. Okay, your answer this time is A. This is the graph of 4 to the x power. It's shifted right 2 and up 3. So our normal point would have been at 0, 1 for our intercept, but we went right 2 and up 1, 2, 3 units. And we find this is that point that we would always have from the parent function of 0, 1. All right, example 3, we've got a real-world problem. This is about graphing exponential growth functions and the amount of people that use the internet. So it says in 2006 there were 1,020,000,000 people worldwide using the internet. At that time, the number of users was growing by 19.5% annually. Draw a graph showing how the number of users would grow from 2006 to 2016 if that same rate continued. So the first thing we need to identify is how many people there were at the beginning and what our rate of growth is. The amount of people at the beginning was 1.02 billion people, and our rate was, if you convert this percentage to a decimal, it's 0.195%. The formula, it doesn't appear that they're going to tell you this off the beginning, but the formula for exponential growth is y equals a times 1 plus r to the t power. T is time, r is your rate, a is the amount of people, or whatever you're starting with, whatever the concept is. So we have 1.195 because we're doing 1 plus the rate and the rate was 0.195. A is 1.02 billion, and t is time. Once we graph our function, we're then going to see what would happen in 2016 if that rate continued. This is probably something you want to look at on your calculator, because obviously these are crazy numbers that you wouldn't see normally on a graph. Billions you probably don't normally see. But the function looks like this. So in 2006 there was about 1.02 billion. If we follow that pattern out to 2016, it predicts that there's going to be about 6 billion people using the internet in the current year that we're in right now. Okay, so here's a check your progress problem, pretty much the same concept. Pause the video as long as you need, and when you have your answer, go on to the next screen. Okay, our answer this time is D. Pretty hard to see. Let's see if I can zoom in. How can I zoom in? There we go. So D, the y-axis is cell phone users in billions, starts at 2, and we have the year 2006, and we're counting by 2-unit increments on our graph. Okay, we're going to pause here and pick up with exponential decay in the next video.